Welcome back. Topic 2. Heat equations for internal flow convection. You will study 12 heat equations compared to only 2 heat equations involved in external flow convection. A. Heat equations that are independent of thermal boundary condition. It indicates that all those equations are valid all the time. This is our system with the defined control volume, mass flow carrying energy enters the control volume at temperature Tmi and leaves at temperature TMO. There's convection between solid surface and moving fluid. This is the energy balance for the defined control volume. The first law states that all energy in equals all energy out. Therefore, equation 1 represents the convection to the fluid flowing in the tube is equal to the increase in the energy of the fluid. If we're interested in the heat flux at a specific location X, equation 2 relates the surface heat flux at the specific location X to the local heat transfer coefficient and the temperature difference between the solid surface and the moving fluid at that specific location X. For example, at the outlet of the tube, X equals L, the surface heat flux at the outlet is defined by the heat transfer coefficient and temperature difference, all the parameters at the outlet. If you're interested in the convection heat flow at the tube parameter of location X, equation 4 relates the surface heat rate per unit length at the parameter of the location X to parameter pi d, local heat transfer coefficient, and temperature difference between solid surface and moving fluid at the parameter of the location X. For example, at the outlet of the tube, X equals L, the surface heat rate per unit length at the outlet is defined by the parameter heat transfer coefficient and temperature difference, all the parameters at the outlet. Please note, in the equation 2, 3, 4, 5, they all use local heat transfer coefficient. B. Heat equations under the thermal boundary condition of a constant heat flux. It indicates that all those heat equations are valid only under this boundary condition. This is our system with constant heat flux acting on the solid surface. Since heat flux is constant, the convection heat rate can be calculated directly from the heat flux and the set surface area pi dl. As a result, there's no need for us to find the average heat transfer coefficient for the convection heat rate. This is the diagram that shows how the flow temperature changes over the tube lengths with temperature T in the vertical axis, location X in the horizontal axis. As indicated in equation 7, flow temperature Tmx is changing linearly with the location X over the tube lengths. If you're interested in the flow temperature at the outlet, equation 8 relates the flow temperature at the outlet TMO to the flow temperature at the inlet TMI and constant heat flux, parameter P, mass flow rate m dot, the specific heat Cp, and location L. Please note, there's no heat transfer coefficient involved in equation 6, 7, 8. Therefore, there's no way for us to know whether the local or averaged heat transfer coefficient involved. C. Heat equations under the thermal boundary condition of constant surface temperature. It indicates that those heat equations are only valid under this thermal boundary condition. This is our system with constant surface temperature, Ts. This is the diagram that shows how the flow temperature changes over the tube length with the temperature T in the vertical axis, location X with location X in the horizontal axis. As indicated in equation 11, the flow temperature Tmx changes exponentially with location X. This straight line represents the constant temperature Ts. If you're interested in the flow temperature at the outlet, equation 12 relates flow temperature at the outlet TMO to surface temperature, flow temperature at the inlet, parameter, average heat transfer coefficient, mass flow rate, specific heat, and location L. Since the flow temperature changes non-linearly over the tube lengths, we have to introduce the log mean temperature difference to calculate the convection heat rate. Equation 9 relates the convection heat rate to the side surface area, averaged heat transfer coefficient, and log mean temperature difference, which is defined in equation 10. In this equation, that TO is the difference between surface temperature Ts and flow temperature at the outlet. That Ti is the temperature difference between Ts and flow temperature Tmi at the inlet. Please note, in equation 9, 11, and 12, they all use the averaged heat transfer coefficient. Next, let's practice on how to select proper heat equation for unknown. D. Example 8-2 for System A. System A is an internal flow convection system with cold air flowing through the hot tube. What we know is the mass flow rate, the heat transfer coefficient, the flow temperature at the inlet, the tube length, the convection between the solid surface and moving fluid, constant solid surface temperature Ts, which is our thermal boundary condition, and tube diameter. We're looking for the flow temperature at the outlet. This is what we know, what we're looking for, and under what boundary condition. Where to start? Let's start with the equations that are independent of the boundary conditions because they're valid all the time. Then we go each equation to identify the unknown TMO, TMO, TMO. Then we check each equation, including the unknown TMO. Since we don't know the convection heat rate, we cross out this equation. Similarly, we don't know the heat flux or the heat rate per unit length. Therefore, we cross these two equations out. Next, we will move on to the equations under the condition, thermal boundary condition of constant surface temperature. Then we go each equation to identify the unknown TMO, TMO. Next, we check the equation, including the unknown TMO. For equation 9 and 10, since we do not know the convection rate, we cross this equation out. we move on to equation 12. Then we check. We're looking for TMO. We know TS, TMI, parameter P. Since we know the diameter, which is pi d, we know the heat transfer coefficient, mass flow rate, specific heat, and location L. This is the equation we selected. From the equation, we know the average heat transfer coefficient is used. E. Example 8-2 for System B. System B is an internal flow convection system with the cold water flowing through the hot tube. What we know is the flow rate, the diameter, the flow temperature at the inlet, the lengths, the constant heat flux acting on the solid surface, which is our thermal boundary condition. There's a convection between solid surface and moving fluid. The flow temperature TMO and heat transfer coefficient at outlet. What we're looking for is the specific surface temperature at the outlet. In summary, this is what we know. This is what we're looking for. This is the thermal condition. Where do we start? To select the proper equation for unknown, we start with the heat equations that are independent of the thermal boundary conditions. We go each equation to identify the unknown TSO. There's a TSO in equation 3 and a TSO in equation 5. Next, we check each equation, including the unknown TSO. Since we know the heat flux at specific location outlet, because heat flux is constant, it includes the outlet location. We know heat transfer coefficient at outlet. We know the flow temperature at outlet. So this is the equation selected. From this selected equation, the local heat transfer coefficient is used. Through these two examples, you noticed the selection of proper heat equation is a trial process. However, only practice can make perfect. At this point, we covered topic 2. We can put this 12 equation into an equation sheet. Through examples, you learned how to select the proper equation for unknown, and from the equation selected, you can determine whether the local or the averaged heat transfer coefficient is selected and will be solved using the roadmap in topic 3. See you next time.